In this video we're going to find the partial derivative of this equation. We're going to find the partial derivative at this location. So let's try and understand what this is saying. So when you have a surface, so you've got this surface here in 3D space. I don't know what it looks like, so let's just imagine it looks something like this. I don't know. Let's just imagine it looks something like this, some sort of surface. So here, here you can see that z would be a function of x and y, because when you input a value of x, let's say 2 and then 3 across, then it would jump to a height of z. So you can imagine z as being a function of x and y. So when you're trying to find the partial derivative of z with respect to x, it means that this is a variable, and so this is also a variable. This y here is a constant. So this this partial derivative of z with respect to x means you have the ability to work out the gradient anywhere along this vertical plane here. So where this vertical plane intersects with the surface, so it could be anywhere along here. Y is a constant, don't forget. And then you've got all these vertical planes. You've got all these vertical planes. Where the vertical planes intersect with the surface, you have the ability to work out the gradient. So partial derivative of z with respect to x means you keep y constant and then x varies. So anyway, this thing here gives you the ability to work out a gradient on any of these planes. Okay, so let's try and compute it. So now imagine this thing here as a bubble. This bubble here is a variable because well, this is a variable because we're trying to find it with respect to x. So we know that this is a variable, this is a constant. Well, this bubble contains a variable, meaning the whole bubble is a variable. So when you come to differentiate it, hang on, oops, hang on. When you come to differentiate it, imagine this as being a bubble. Just remember that this bubble contains a variable inside there, making the whole bubble a variable. So when you come to differentiate it, it would be cos of the bubble, cos of the exact same bubble, and then times the derivative of the bubble itself. So remember, this is a variable and this is a constant. So when you times the derivative of the bubble itself, it would just be 1, because when you differentiate x, it's just 1. So x is an independent variable, so you don't need partial derivative of this with respect to anything, because this is an independent variable. If you have a z, then you need to times by this thing here, but we are not dealing with z yet. So now come to this. Imagine this as being a bubble. Is this bubble a variable? Well, y is a constant. Z here does contain x, because we're trying to find it with respect to x. It does contain x, making this z a variable. Well, if this z is a variable and this whole bubble contains z, then the whole bubble will be a variable. So let's try and differentiate this. So when you differentiate this, it would be cos of the bubble. So it would be cos of the exact same bubble, now times the derivative of the bubble itself. When you differentiate this, it would just be 0 because y is a constant. And when you differentiate z, remember z is the output here. Z is the output, is a function of x. So when you differentiate z, it would be 1. But then because z is a function of x, you need to stick the partial derivative of z with respect to x. So when you come to differentiate this, it will then give you this whole thing here. Now come to differentiate this. Imagine this thing here as being a bubble. So this is a variable. This is also a variable, meaning this whole bubble here will be a variable. So hang on. So imagine this as being a bubble. When you differentiate this, it will be cos of the exact same bubble, then times the derivative of the bubble itself. Well, the bubble itself, when you differentiate this, it will be 1. And don't forget, x is an independent variable, so we don't need the dz by dx thing. We just need to differentiate it because it's an independent variable. So let's start again here. imagine this is a bubble here. When you differentiate it, it will be cost of the bubble, and then you times the derivative of the bubble itself. When you differentiate this, it will be 1, and then plus, differentiate this. When you differentiate z, it will just be 1, but then because z is a function of x, you need to stick partial derivative of z with respect to x. So that will then give you this thing here. Well, when you differentiate this, it would just be 0. So that will then take us to here. So now tidy this up. Hang on. So tidy this up. Hang on. Tidy this up. So this whole thing here will just become this, and this whole thing here will just become this, and then you've got one block. You've got one block multiplying this block here with a plus in the middle here. So that means you've got to get this times this. That will then give you this, and then this times this. That will then give you this. And remember, we're trying to isolate partial derivative of z with respect to x. Partial derivative of z with respect to x. So we want all these. Well, at the moment you've got this block plus this block plus this block plus this block equals this block. You want to group all these together on one side, and throw these on the other side. So take away cos x plus y, and then take away this block to the other side. That will then give you this, and then factorize out the partial derivative of z with respect to x. So this thing here will then give you this, and then this thing here will then give you this. So do it all in one go. Alright, so from here jump to here. So that will then take us to here. You want to get partial derivative of z with respect to x on its own. So divide both. So at the moment you've got one block times this block here. So to get this on its own, divide both sides by this. So that will then give us this thing here. So partial derivative of z with respect to x, we want to evaluate it at this precise point here. This is x, y, and z. So put this into the x, put this into the y, put this into the z, and so on. So the partial derivative evaluated at precisely this point here at pi, that will then give us this thing here. Well, cos of 2 pi is 1. Cos of 2 pi is 1. So it's negative 2 over positive 2. So that will give us a gradient of negative 1. This is your final answer. Okay?